So first, I would like to thank Rushi and CIG for inviting me and for giving me this really great opportunity to present my work, and especially the visualization component of my work. Today, I will try to show you a little bit of how to combine modern geophysical data sets and even numerical models with 3D printing and virtual reality to generate some innovative outreach activities. Before start, I would really like to thank the Visualization Lab interns during the last years. Many of them had SCEC internships that helped me with the generation of all these activities. And I will also have to thank the William, Josiah, and Ionas that they did their capstone project as undergrads in my Vis Lab in the spring 2024 semester. So before we go on, just a little bit about what I do and what is my job. And what I do is that I study earthquakes and in general the earthquake cycle. But in reality, this schematic animation is just an excuse to remind you what to do during an earthquake and drop cover and hold on. Now, more specifically about my work, during the last years, I was mostly working with a numerical models, specifically what we call dynamic rupture models. And this is a video simulation of two of these models, basically here. Those are basically computer-generated earthquake rupture scenarios. And they are, first order, we can say that they are divided in two parts. There is an initial phase. I will move back the video for a second here. The nucleation phase, as you see here. And then there is a second phase that is the spontaneous propagation phase, where a rupture propagates across the fault network and allow us to observe, for example, interactions between faults. In this particular case, we were experimenting with the tendency of the cross faults, the rupture tendency of the cross faults during these scenarios, and trying to figure out how these cross faults that are implemented in the middle of the domain affect the overall rupture. And at the end of this video, you can see that, the top simulation over here basically had more slip than the bottom one. And that was just the result of how these smaller faults interact with the larger structures. And basically, again, as I said, these models are extremely useful because they allow you to run large earthquake rupture scenarios to evaluate the effects of future earthquakes. And now, as we can see, obviously here, we are dealing with complex models. As a geophysicist, geoscientist, earthquake scientist, we deal with the earthquake processes that are extremely complex. But in one sense, it's also complicated to communicate to the public what we do in the advanced part of our research. And so what I have found in the past is that many of the demonstrations about earthquakes often oversimplify the complexity of the real world and not always properly reflect the significant efforts and achievement done by our community, by the earthquake scientists. So, I always had this idea that more could be done to represent and communicate the cutting-edge aspects, specifically the top part of our research, and further raise awareness in the community and engage the public in our discoveries. And so here's a little bit the outline of today. There is a first part that I probably already did, the inspiration and motivation behind the Visualization Lab. Okay, it's to generate these innovative outreach activities that will help us communicate to the public the advancements of our research. And I'm going to talk about the methods that I use in the softwares to make large 3D print models, how we use them in outreach and education activities, and as well, the same thing I will do for the virtual reality environments. So what we see here is a Uniform California earthquake rupture forecast model. This is basically a mathematical model or probabilistic models that allow us to estimate the likelihood of rupture along major faults in California. And it's a collective effort, of a diverse pool of scientists, so 40 or 50 years of work to actually identify all these fault segments. And, what I was most interested from this model and I was attracted to was how nicely represent the complex fault network in California around the San Andreas. And this particular model here has over 300 fault segments. And I was lucky at the time when I was at the University of California, Riverside, to work with Keith Richardinger and Jim Dietrich, that they were already using the geometry of user-free for their earthquake cycle simulations. So this model gave me the opportunity to generate a new type of outreach and education activity. What I did is that I generate a large 3D printed model, and I started from the facet, the .fac type of files, that is a triangulated, basically, representation of the faults. I scaled the model from, of course, the UTM kilometrical coordinates to something smaller, because I will have to, in the end, we will have to 3D print it and go through an operation that is called thickening, necessary before 3D print, and then generate the STL format, which is what the 3D printed reads in order to start the printing operations. So I would like to give just a little bit of explanation about how we do this, and especially in a larger scale. So this is here we see, for example, the numerical model that is still right now on our computer. What we have to do is that we have to perform this thickening operation, because in order to print something, it cannot be very thin, but it has to be at least, let's say, 2 millimeters of thickness, all right? And that's for the average home office type printers. Obviously, there is technological printers that cost several $1,000s that can do very thin, they can print very thin layers, but this is not the type of printer we do here. So, and when basically we have this thickening done, you can see that the faults, basically, the actual faults are in the middle of the volume. Okay, this is how we basically represent a fault. We create a thicker volume, and the fault, it's right in the middle of that. So after the thickening, what we have is a 5 feet or 1.5 meters long model that sits right now, again, still on our computer. And we have, however, in order to be able to 3D print it, to divide it in many groups. And each of these groups requires a different 3D printing time and a different amount of 3D printing filament. Now, the reason we do that is that still today, the average 3D printer for the home or your office, it's going to be around 20 to 25 centimeters printing bed. So you have to break down the model to fit the printing bed. Although there is also larger printers today, but if you want to print something large, again, you have to break it in several pieces. And, here, for example, this part here, the shear zone of California down here, it's because I chop off that part, I was able to, make it fit it basically on the 3D printing bed nicely and without big troubles. But when you're trying to print something like that, then you have basically to squeeze and regroup everything. So it's kind of a time-consuming operation, but I'm pretty sure there is very smart people out there that at some point they will make this automatic somehow, okay? And you're going to run an algorithm and it's not difficult to do it. You run an algorithm, reads the faults, and basically group them in an optimal way for you to 3D print. And so in the end, I had these 12 groups that represent the model. And we 3D print each of these groups for approximately 120 hours total 3D printing time. and about a kilogram of filament. 120 hours, of course, is if everything goes smoothly. If you are, if you are learning, if you are relatively new to 3D print, or even if you're not relatively new, sometimes 3D printing operations fail. And so it probably, when I say 120 hours, it might be more if you have to repeat printing of a piece, if the operation failed, right? Today, there is 3D printers that have cameras with AI software. Now they will actually send you an alert that something is going wrong with your print. But back in 2017, when I printed that model, and I have to recognize that this the first model was printed at the Creator Lab at the University of California, Riverside, with Michelle Potter, that she was the manager of the lab at the time, and really adopted my project and helped me. And we used the Maker Replicator 3D. The total cost, it was about $50–60 as material. We're talking about now material. I would like to show you how 3D printing looks like for a fault system. I don't have a video from the MakerBot replicator. I'm showing you a video from a new printer I bought last year, the Creality CRM4, that, as you can see, it has a significantly larger printing bed. Okay, so I made, because up to now I have printed probably 3 of these 5-foot-long user-free California models. That was the second, I think, maybe 4. That was the second one I printed here in Memphis. It was a little bit cheaper because the material used for the first was from the company that produced the printer. But anyway, there is cheaper options, and this time was more about $30 in total. So the final product is, again, a 5-foot-long model with 300 fault segments representing the complex fault system developed around the San Andreas fault, okay? And it's like a Lego, basically. You can break it in pieces, actually. And that's what makes people also that they like to try to move around some of these pieces, see how they match. And the model resides on the top of a map made with GMT, and includes also the major cities and some of the locations in California. And it's relatively light. It's transportable. And it's light, it's transportable. And I actually have even a mini version that I will show you later. So let's move on. All right, let me see the slide next. Okay. Over the years, I have used these displays in many, many outage events. When I was back in California at UC Riverside, I probably did at least 50 events. And what better occasion from the shakeout day, right? So this is two examples. On the right-hand side here, on the right is shakeout day 2017 on campus, with a lot of our graduate students helping. You can see Baoning here, Jilia and other people, talking to students. The 3D printed model really captures the attention of people. And on the left here with my colleague Gareth Fanning, we are outside the LA City Hall. That was also a great day. And I made one of these smaller ones for actually the mayor of LA at the time. And you can see, kids really love to play with this and learn. So, something I will say actually proud is that we were actually invited with David Oglesby to go and take part on a congressional field hearing with a 3D printed model. And over here, you can see Congressman Mark Takano with a smaller version that we made for them. And, he was using it during the discussion of this hearing. It's really amazing how much people can learn from something like that. But for me, it was extremely interesting to use it to interact and have discussion with policymakers and the elected representatives. It's really, really a great tool, and we have really fun that day. In class, here I'm with Obigos. This is a class that I also taught one time when I was back there, but this was Obigos class. I went a couple of times. It's earthquake country, so GO008. So it's a class when they learn about earthquakes. And, we put it in class and students will come around and ask us questions. And basically we based a part of the class on the 3D printed model. And many other academic and scientific events that I did at that time. All my colleagues helped me and embrace this new type of, let's say, displays. And I even did a TV interview here on the left. So, okay. Now, benefits from using the 3D printed display. There were a lot of benefits. Our academic booths become really more attractive, and it draws people attention because it's like a toy, it's like a Lego. People want they ask you, what is that? How you made it. And yes, the presence of the model increases people's curiosity. People ask more questions when we use these models. Okay. It obviously brings enthusiasm, and facilitates the conversation. They are more encouraged somehow to ask a question. And they definitely change how non-experts learn about earthquake hazard. And here's something very important, provides a remedy to common misconceptions about earthquake faults. And specifically, here's what we learn. We learn that by using this model with our visitors, we help them solve 3 common misconceptions. The first one was that most people in California believe that in California there is only one fault, the San Andreas fault, but this is not true. It's a complex network of faults. And that was the model have this power, revealing power to show that. The biggest misconception of all, however, was number 2, that most people, pretty much everybody that is not an expert, thought that faults are either a line on a map or a vertical plane. And they were surprised to know that actually, like here in the LA Basin, there is dipping faults that intersect other faults. And there was another misconception about many people realizing that not all faults reach the Earth's surface, and that is blind thrust. Recently I 3D printed a more detailed version of the Southern California fault system, the SCEC CFM model. I'm not going to spend much time right now over here, but this is, now that SCEC is actually statewide, we have also CFM7 that extends to the north, and so soon I'm going to complete the printing of the community fault model that is more detailed than the previous, than the user-free to Northern California. But you really can appreciate, again, look, this is all work that our colleagues have done in the last 40, 50 years. Of course, I have to thank the CFM group at SCEC for doing such an amazing job, in creating the data set and the 3D model. Okay, because obviously I did not find all of these faults by myself. I was given this great data set and the opportunity to use it. And this is just, that was just to show that my new printer has a larger printing bed and I can make larger pieces. Although printing larger models for longer time might have some disadvantages sometimes. And I forgot to say, actually, that model here, it takes more time to print it in total. It took at least 200 hours to print the whole thing with one printer. Okay, now, here's another great question. You show us, you can say that you print faults, but can you print earthquakes? Can you print seismicity? Which is actually extremely important for where I am based right now. I'm a professor at CERI, the Center for Earthquake Research and Information in Memphis, in the new Madrid seismic zone. And in the new Madrid seismic zone, it's seismicity that really tells us where the faults are. And so can we print clusters of seismicity? It was one of my goals, something I wanted to try. Okay. And yes, after figuring out some things, we did 3D print earthquakes, clouds of seismicity, together with the new Madrid seismic zone faults, right? And that brings really an additional level of scientific information for our visitors and for the people that we are interacting with when we do outreach, when we do communication, when we're going to talk to the policymakers. So this is just the videos show, 3D printing of a strike slip fault, the axial fault, and a thrust fault over here. So let's see the final result. It's a 4-foot long model of the main New Madrid seismic zone faults, which are the axial fault over here, okay, and the rail foot thrust. And here I will have to really highlight the importance of using the seismicity published, relocated seismicity, 20 years worth of relocated seismicity published from Ji-Xin Zhang, that she was actually a graduate student here, published this great JGR paper that gave me the opportunity to nicely show lineaments of seismicity together with the faults. So I downloaded the data were available through the JGR paper, and I put it together with a fault system that I was already using for a set of dynamic rupture simulations. That was the first opportunity we have to use it, Earth Day in May 2024. We have approximately 100 middle schoolers coming for this event and, really learning about, in a tangible way, in a tactile way, that they live close to a major fault zone, the New Madrid seismic zone. So now, I will actually stay here. Here's one important question, however, is the following. Do we believe that we can actually do more in helping people exploring these 3D structures, all right? So these models, they are fantastic. They are great. You can play, but they are kind of static in the sense that there is a component of exploration that is missing. Because yes, you can take them and rotate them with your hands, but they also, I noticed by doing a lot of outreach events, they still create some misconceptions to people about the scale of things, obviously, right? Because even these models have scales, and we tell them, this is about 10 kilometers, this, segment here. We do have a scale in these models. But still, I believe there is a problem with understanding how big are these structures. And so what I did some years ago is that I started experimenting with 3D printed with virtual reality, okay? And look how we can make the 3D printed model into a virtual reality activity. Okay, here I am with my graduate student Ivan, together jointly inside the California fault system, the one that is 3D printed here. And VR gives the possibility, of course, of changing the scale, right? So I can be from, a short investigator that is approximately the same size of the faults to be a giant like this. So it really helps you, of course, flying through the experience, definitely. You really become a virtual explorer, but also changing the scale. And the tool we were mostly used during the last years to do these VR activities is ParaView. And this software was extremely useful for us because ParaView is a software for scientific visualization that many people use, but it also has an OpenVR plugin that you can activate it in the software, and then your scientific data, and you can explore your scientific data through virtual reality. And it's, in my opinion, it's very user-friendly in that sense, in the sense that doesn't require to write a computer code like you will do for a game engine like Unity. And, ask me please if you want at the end of the talk. We also have, we have been also working with a Unity that is a more advanced software. But ParaView really has this possibility, you take your numerical models of your data and you can make them in a VR world in a relatively short time, right? And so the model we put up here had, the faults, and the faults are called by depth. And we had many things. We had the counties, seismicity, hydrologic information, many things were implemented. And you can become a virtual traveler. Now, sorry about that. The next important thing that is also available with ParaView, and it's extremely important, is the joint exploration. So ParaView allows you basically to do a remote VR session. Let me pause it for a second. What you can see here, it's me connected from the visualization down here. It's down here, all right? Arushi, can you see the mouse pointer here?
Yes, we can see that.
Okay, you can see that, right? Yeah. So this is me connected from the visualization lab. Michael and Diane, my first two interns here in Memphis, during COVID, connected from their house into the same VR activity with me, okay? And they really helped me a lot to explore this possibility at the time, to see how this works. And together now we are flying into the California fault system to do basically a virtual field trip. And again, always during COVID. It was a really great experience to test this tool. I'm gonna push it a little bit forward here, okay? Right, so as you can see, we are under the fault system together. At some point, and this is from my point of view. In fact, yes, when I turn here, I can see the avatars of Diane and Michael follow me. Like I will take them around through the faults and also, go under the LA basin and explain things about fault dips or fault strike. I mean, these two students, they were amazing what they were doing with me, and they were computer scientists, right? So, but ParaView gave us a possibility to actually do these field trips. And we have done presentations at SCEC and AGU. We really did great in presenting this work. So, a little bit about the systems we use. I have tested a variety of goggles. And today you can buy goggles from, the cheapest ones, I believe, would be from $200 to $400. I mean, they are still expensive, but not expensive as this one, for example, the HTC Vive Pro, that was the first one I bought here. And so we have a setup here where in the Viz lab, I have, let's say, a fixed system with a desktop, an Alienware desktop. And I also have a mobile, let's say, system where I use a laptop, a VR-ready laptop with goggles. And that can be used also in a classroom, of course. Now, let's say, the important part here, when you want to use your goggles and connect them, basically being able to visualize your work through ParaView, it's this free software that is called SteamVR. And this is basically a software or libraries that you can install. You have to install on your PC. You have to install your PC. And when this is done, it's relatively easy and straightforward to basically use ParaView as a VR platform. Like we have installed it on many computers, really never had major issues, right? So what I'm trying to say is that combining ParaView with SteamVR and pretty much any goggle system, it's something that can be achieved relatively easy. Well, yeah, this is the first case where we actually use this VR, remote VR possibility. Again, my interns at the time, Diane and Michael, they went in the Soto Central High School in South Haven, Mississippi. They did a great job organizing some VR games with the students, with the high school students. But the highlight was that we did a remote VR connection. So I was connected from my visualization lab, and I took into a virtual trip of California a student at the Soto Central High. So we were, in different geographic locations. So again, this shows the possibilities, of this technology, because obviously we are studying earthquakes and we are exploring faults, but you can apply this to everything. You can apply this if you have a numerical model of the human body or buildings, anything. You can do remote sessions. Right, that was another case, the White Station High School. I just want to emphasize that, because Diane definitely was very helpful at the time to organize these events. All right, here is something else that came up during the development of these VR activities. What I noticed, again, is that with the 3D printed models and even the VR activity, it's not always easy for non-experts to realize the scale of things, right? And so I thought that something extremely helpful is to start adding the human environment on top of these fault systems. And that's what we did. We worked together with Katina Carranza and Kati Barajota, my SCEC interns last summer, to start adding layers of basically the cities. Actually, I should recognize that one of the students, Dionas, doing his capstone project in the spring, he was actually also, spent some time on looking into this topic in my lab. And basically now you have the possibility to fly into the VR world and realize that if a skyscraper it's 100 meters, the width of the fault can be 150 times that. So it really gives you the idea how big are these faults. Even for me that, I'm a geophysicist, when I really did that, I said, okay, the fault system, these structures are really big. They really show how big they are beneath the human environment, the houses, the landmarks, the buildings. This is something we are still working on right now, because it wasn't really easy to, import these human built environment layers, and we're still working on that. And to go at all these previous activities that I show you, they are from one point of view static, in the sense that there's no, propagating waves. You don't actually see the earthquake rupture. I'm talking about the VR activities. So what I'm going to show here through an electronic HU poster, and I'm actually going to exit to go to the poster. All right. And this is available in the chat. Please go and check it, and let me know if you have questions. But the poster was presented in 2022 at AGU and summarizes nicely our VR activities and what you can learn from these activities. Something I would like to mention over here is that back in fall 2022, and this fall, actually, I taught basically the first VR kind of based class at the University of Memphis, where I had a group of undergrads, first-year students, and teach them how to use virtual reality to represent scientific data. These students, actually, they are not geologists. They are from all different backgrounds. And the goal of the class was to encourage them to use virtual reality, or more in general, modern visualization techniques to represent scientific data, okay, and communicate this to the public, or communicate, generally the research. Something fun also over here is that if you look at the video, you will see the avatars of the students. So I have 5 of the students basically to get all connected at the same moment inside the same virtual reality experience and take them on a tour again of the faults. I should also mention that we have a preliminary virtual reality model of the new Madrid fault system. So we don't have to always use California. All right. But what about the possibility? What about the possibility to experience, something more dynamic from the earthquake point of view? And so what we can see here is that, again, with ParaView, we built an activity where you explore basically a dynamic rupture model. Okay, so you became a virtual traveler inside this synthetic rupture, right? This specific activity showed the 2010, it's a numerical model, it's a dynamic rupture model that I published on a paper in 2017 and shows the El Mayor Cucapa earthquake in Baja California in 2010. This specific activity, it's very useful in doing the following connection, in learning how fault slip rate, so how fast the two sides of the fault move, transfer into ground motion, and how actually the geometry of the fault plays a role into that. And so if you go again in my electronic poster, I have explanations about, for example, what is presented here in this video activity, what type of simulation output is included, how I can learn by playing with this activity. There is all this information that you can look. And there is another nice example. I have like a model of the basically Bay Area with the rupture of the Hayward fault kind of over here. Yeah, right. And you can find other things. This is actually down here. Oh, I thought I had a different model, but anyway, yeah, there is also this activity with the Hayward fault. Okay, so now let me exit. I'm gonna go back to the presentation. I think I'm pretty much done right now. What I want to tell you is that please visit my website because there is many more models you can see over there, right? And send me an email. I'm happy to chat. I'm happy to meet online and talk about these models or how you can build your own models. This is my website. Besides, of course, the research part, I have a specific session for 3D printing, BizLab, and outreach. And thank you again for inviting me to present my work.